Okay, good morning. Today we are going to start with the central object of our study, which is qubits. So in this lecture we'll start with an introduction to qubits and to two of the very basic axioms of quantum mechanics, the superposition principle and the measurement principle. And then as an exercise, what we'll do is talk about a very simple uncertainty principle for qubits. Okay, so let's get started. So quantum mechanics, where the name comes from is this concept of quantization, which is that certain quantities, such as energy, get quantized when you're working with for instance, with electrons in an atom. What it means for these quantities to be quantized is, unlike classical physics, where the energy of a particle is just an arbitrary real number. Here, when the electron is in an atom, its energy can only take on certain discrete prescribed values. So here's a simple sort of picture of it. So imagine that this is a picture of the electron of a hydrogen atom. So the solid dot here is the nucleus, and then these dotted lines here represent possible orbits of the electron. And of course, this is a very simple schematic, but it's meant to represent this fact that the electron cannot just be in any old state. It must be either in the ground state or in this first excited state or the second excited state and so on. And each of these has a discrete energy level. Okay, so this phenomenon of quantization occurs when the particle is confined, and we'll say a little bit about this later in the course. But for now, we want to think of a system which can be in one of finitely many different states. So imagine that you have a hydrogen atom, and the energy of the electron is bounded, so it can be in, let's say, in one of these three states: ground, first excited, or second excited. Okay. So in general, we have a k-level system. So we were in the example we were thinking of k as 3, and the possible states of the system we are labeling as 0, 1 through k minus 1. Okay, so in other words, for example, if k were 2, then we could use the state of the electron classically to represent a bit of information. Okay, so what are the possible states of the quantum system? And this is where this very strange principle comes into play. It's called the superposition principle. And what it says is that the electron in general doesn't make up its mind which of these k distinguishable states it's in. In fact, what it is in some sort of superposition of all k simultaneously. Now, the superposition is very hard to picture, and but mathematically it's very easy to describe. So what the superposition is it's described by specifying a complex number for each of these possibilities. So it's in the ground state with probability amplitude alpha 0, where alpha 0 is some complex number. And it's in the first excited state with probability amplitude alpha 1, and so on. Now, we'll also require that these probability amplitudes are normalized. So the sum of the squares of the magnitudes of these amplitudes is 1. So let's do a simple example. So for example, if k were equal to 3, and let's say all these amplitudes were equal. So for example, we could have a superposition 1 over square root 3, 0, plus 1 over square root 3, 1, plus 1 over square root 3, 2. And you can check that this is normalized because the sum of the squares is 1. Now, of course, you can also make one of these. These can be arbitrary complex numbers, so you can have a negative sign here, or you could make this I over square root 3, where I is the square root of -1. Right, so it's an imaginary number here. Or you could make it, for example, be the case that the superposition looks like this. It's 1 over 2, 0, minus 1 over 2, 1, plus 1 over 2, plus I over 2, 2. And of course, just make sure you remind yourself how complex numbers work. So the magnitude of this complex number is 1/2. The magnitude of this one is 1/2. So when you look at the square of the magnitude, you get, in this case, you get a quarter. You get a quarter. And the square of the magnitude of this complex number is just the square of the real part plus the square of the imaginary part. So you get a quarter plus a quarter, which is 1/2. And all that sums up to 1. Okay, so that's the superposition principle. Now, mathematically it's very simple. All it says is you describe the state as this linear superposition. But what does it really mean? And, what does it mean that there are these complex numbers associated with each of these possibilities? And what does it mean that the state of the system is this linear superposition? One way to think about it is, this is what we saw last time with the double slit experiment, where the electron went through each of the slits with some complex amplitude. Right? So these are the same complex amplitudes. So that electron was in a superposition of going through slit 1 and slit 2. This electron is in a superposition of being in the ground state, first excited, second excited state. Another way to make sense of this is by understanding what happens when you actually measure this electron. So when you go to measure this electron, in fact, you don't see it in a superposition. What happens is the electron quickly makes up its mind which of the k classical states it's in. And the way it does that, the rule according to which it does that, is that what you end up seeing is that it's in this jth state with probability alpha j magnitude squared. Okay, so you take the square of the magnitude of this amplitude, and that's what's the probability. So it's a good thing that the squares of the magnitudes summed up to 1, because these are really mutually exclusive possibilities, and the probabilities add up to 1. The second thing to know about this, which is very strange about this setup, is as soon as you make the measurement, if the outcome is j, that's the new state of the system. So the superposition disappears, and what you're left with is that the new state of the system is j. So for example, if the state of our system was 1 over 2, 0, what did we have last time? We had 1 over 2, 0, minus 1 over 2, 1, plus 1 over 2, plus I over 2, 2, and we make a measurement, then the probability that the outcome is 0 is a quarter, and if this is the outcome, then the new state is 0. The probability of 1 is also a quarter, the new state is 0, is 1, and with probability, and the outcome is 2 with probability 1/2, and if so, the new state is 2. Okay, so now you can ask, what, this is sort of a funny thing, that the quantum system is in some state which is this linear superposition, which we have a hard time picturing. And then it's only when we look at it, if we measure it, that the state collapses into one of these distinct possibilities, one of the k possibilities. With this simple rule, so the rule is simple, but how to interpret it is very problematic. And the reason it's problematic is that nothing in our daily lives, nothing in our study of classical physics or in the world around us, in our interactions with the physical world around us, prepares us for something this strange. So the great physicist Richard Feynman once said that nobody understands quantum mechanics. And what he meant is that it's hard to understand this intuitively. Now, one of the beauties of learning quantum mechanics this way in terms of qubits is that it's a very simple system. There's very little going on in these k-level systems. And so it exposes these paradoxical elements of quantum mechanics right up front. Okay, so for those of you who are seeing it for the first time, this is the mysterious part of quantum mechanics, with nothing hidden from you. Okay, finally, I said that we were introducing qubits. Well, qubits just happen to be the special case of k-level systems where k equal to 2. So imagine that the electron can either be in the ground state or the first excited state, which you represent by 0 and 1. You can use this to store a bit of information. Ground state is 0, first excited state is 1. And then the general state of the system, as before, is some linear superposition like this, where 0 and 1 have some complex amplitudes, normalized suitably. And if you make a measurement, the system quickly makes up its mind whether it's in the ground or excited state with probability square of magnitude of the corresponding amplitude.